Assalamu alaikum and very good evening to all of you. In this video, I'm going to derive minor rate of technical substitution between the two inputs and the elasticity of substitution under two production functions, that is Cobb-Douglas production function and constant elasticity of substitution production function. The scheme of the presentation is that I'll introduce the Cobb-Douglas production function and then I'll calculate Malner rate of technical substitution, that will be followed by the elasticity of substitution for the Cobb-Douglas production function, and after that I'll introduce the CES production function, and then I'll calculate Malner rate of technical substitution for CES production function, and finally elasticity of substitution for the CES production function will be calculated, and at the end of this presentation I'll conclude this. So let us suppose that the production function is of Cobb-Douglas form, which is equal to x1 raised to the power alpha times x2 raised to the power 1 minus alpha. This is a multiplicative production function. So if we take the partial derivative of this function with respect to x1, that will be equal to marginal product of x1, and taking partial derivative of this function with respect to x1, we have alpha times x1 raised to the power alpha minus 1, x2 raised to the power 1 minus alpha, and simplifying that is equal to alpha times x2 divided by x1 raised to the power 1 minus alpha, and that is equal to marginal physical product of x1, and let us suppose x1 is labor. If we take partial derivative of the above function with respect to x2, let us suppose x2 is capital, then the partial derivative of this function is equal to this statement, and if we simplify, then we have 1 minus alpha times x1 divided by x2 raised to the power alpha, and that shows marginal physical productivity of capital. It follows that Malner rate of technical substitution is equal to this statement, which is the ratio of marginal product of labor divided by marginal product of capital, and if we simplify this, then finally we have alpha divided by 1 minus alpha, which is constant, times the ratio of x2 to x1. Malner rate of technical substitution measures the slope of an isoquant. If Malner rate of technical substitution is high, then it means that the slope of the isoquant is high, and vice versa. But elasticity of substitution for the Cobb-Douglas production function measures the curvature of the isoquant. More specifically, the elasticity of substitution measures the percentage change in the input ratio divided by the percentage change in the Malner rate of technical substitution, with output being held fixed. So if we let that delta x2 by x1 be the change in the factor ratio and delta MRTS be the change in the Malner rate of technical substitution, we can express this as follows, and that sigma gives us the elasticity of substitution, and that is equal to percentage change in the input ratio divided by percentage change in the Malner rate of technical substitution. So this is relatively natural measure of the curvature, and it asks how the ratio of factor inputs changes as the slope of isoquant changes. So if the small change in the slope gives us a large change in the factor input ratio, the isoquant is relatively flat, which means that the elasticity of substitution is large. In practice, we think of the percentage change as being very small and take limit of this expression as delta goes to 0. Hence, the expression of sigma becomes as follows, and that is equal to MRTS divided by input ratio times change in input ratio divided by change in Malner rate of technical substitution, and finally we have a change in the natural log of the input ratio divided by change in the natural log of marginal rate of technical substitution in absolute. The absolute value sign in the denominator is to convert the marginal rate of technical substitution to a positive number so that the logarithm makes sense. So keep this in mind. We have seen above in the previous slide that marginal rate of technical substitution is equal to the negative of alpha divided by 1 minus alpha times the input ratio. So x2 divided by x1 is equal to minus 1 minus alpha divided by alpha times MRTS. And it follows that natural log of the input ratio is equal to natural log of 1 minus alpha divided by alpha plus natural log of MRTS in absolute. This in turn implies that the elasticity of substitution is equal to the change in the natural log of the input ratio divided by change in the natural log of MRTS, and that will be, if you simplify that, that will be equal to 1. Hence, the elasticity of substitution in the Cobb-Douglas production function is equal to 1. So keep this in mind. Now I will discuss the elasticity of substitution for constant elasticity of substitution production function. The constant elasticity of substitution, that is CES production function, is of the following form, where y is equal to alpha 1 x1 raised to the power rho plus alpha 2 x2 raised to the power rho whole raised to the power 1 by rho. So this is the generalized form of the Cobb-Douglas constant elasticity of substitution production function. And it is easy to verify that CES function exhibits constant returns to scale just like Cobb-Douglas production function. Cobb-Douglas production function also accords to constant returns to scale. So it will probably not surprise us to discover that the CES production function has a constant elasticity of substitution. So it means that if we calculate elasticity of substitution for CES function, that will be constant. To verify this, note that the marginal rate of technical substitution is given by minus times x1 divided by x2 whole raised to the power rho minus 1, so that x2 divided by x1 is equal to MRTS raised to the power 1 divided by 1 minus rho. If we take natural log on both sides, we get natural log of x2 divided by x1, which is equal to 1 divided by 1 minus rho natural log of MRTS. Applying the definition of using a logarithmic derivative, we get that sigma, that is elasticity of substitution, is equal to 1 divided by 1 minus rho. As I mentioned, this is constant, and the elasticity of substitution depends upon the value of rho. If rho is equal to 1, then the elasticity of substitution is equal to infinity, and we have a linear production function where the isoquants are straight line and negatively sloped, and they are parallel to each other. If rho is equal to minus infinity, then sigma is equal to 0, and we have fixed proportion production function, just like Leontief technology or Leontief production function. If rho is equal to minus 0, then sigma is equal to 1, and that gives us elasticity of substitution, which is equal to 1, and in that sense the CES function is equal to Cobb-Douglas production function. So in case of Cobb-Douglas production function, the elasticity of substitution is equal to 1. Ladies and gentlemen, in this video I discussed the derivation of marginal productivities of the two inputs, marginal rate of technical substitution, and the elasticity of substitution for the Cobb-Douglas production function, which is equal to 1, and the elasticity of substitution for the CS production function, which is equal to 1 divided by 1 minus rho, and that is also constant. If you like this video, kindly subscribe to this channel, and don't forget to click on the bell icon so that you can get regular notifications about my other videos that I'll upload for you. Kindly share various videos of this channel in various WhatsApp groups and social media so that these could reach to the maximum possible number of people. Thank you, and